In the earliest moments after the Big Bang, our universe experienced something extraordinary, an episode known as cosmic inflation. This was not just expansion. It was expansion at a pace so staggering that space itself doubled in size again and again in mere fractions of a second. In less than a heartbeat, the universe ballooned from smaller than a proton to something far larger than a galaxy. This sudden surge set the stage for everything that followed: the formation of stars, galaxies, planets, and ultimately life. The reason inflation was proposed is because the universe, as we observe it today, is astonishingly uniform. When we look at the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang, it appears nearly the same in every direction. Without inflation, regions of space that seem identical would never have had time to communicate with each other, since light couldn't travel between them fast enough. Inflation solves this horizon problem by stretching a tiny, uniform patch of the early universe to cosmic scales, ensuring that distant regions look alike. Inflation also explains why the universe is geometrically flat, meaning parallel lines remain parallel over cosmic distances. Without it, the universe could have easily curved like a sphere or a saddle. Inflation smoothed out any initial curvature, giving rise to the flat cosmos astronomers measure today. This solved what is known as the flatness problem, another puzzle in cosmology. Yet inflation was not perfectly smooth. Tiny quantum fluctuations, microscopic jitters in energy due to the uncertainty of quantum physics, were stretched during inflation into vast ripples across the universe. These ripples became the seeds of all cosmic structure. Where the fluctuations were slightly denser, gravity pulled more matter together, eventually forming galaxies, clusters, and cosmic webs. In this way, inflation not only explains uniformity, but also accounts for the diversity and complexity of cosmic structures we see across the skies. The strongest evidence for inflation comes from the CMB data. Sensitive satellites like COBE, WMAP, and Planck have mapped faint temperature variations in the CMB, and those patterns match precisely what inflation predicts. These tiny variations, differences of only 1 part in 100,000, trace back to those quantum fluctuations magnified to cosmic scales. They form a fingerprint of inflation written into the oldest light in the universe. While the idea of inflation is powerful, many questions remain. What exactly drove inflation? Was it a field of energy, a new particle, or something beyond our current theories? Did inflation happen once, or could it have triggered multiple bubble universes in a larger multiverse? These mysteries keep cosmologists searching for answers, pushing the boundaries of both physics and imagination. Cosmic inflation, then, is more than a theory about the universe's first breath. It is the reason the cosmos is vast yet structured, uniform yet diverse. It bridges the gap between the quantum world and the cosmic scale, showing us how the tiniest fluctuations can give rise to galaxies and stars. In a profound sense, it reveals how the universe went from nothing but chaos to a cosmos filled with order, beauty, and possibility.